the quantum nature of smell and vision. So just an introduction to quantum biology. So why quantum biology, right? So I know Dr. Kaczynski talked about how Erwin Schrödinger was kind of the first one to spearhead this concept, even though quantum mechanics has existed since 1838. It took to 103 years later until quantum physics was integrated into biology. And so why do we need quantum biology? And so one reason is the traditional models for biology aren't really comprehensive, and they really miss the mark and they fail to explain certain experimental anomalies. And so this is the major problem that in terms of just receptors for for vision and for smelling, is that we can't really observe them when we take them out of the cell. They kind of spontaneously denature instantly. So this is something to think about. Okay, so this lecture is going to be broken down into two parts, right? So first we're going to do olfaction, which is smelling, and then vision. So for quantum nature vision, there's two theories, right? This is the traditional one, non-quantum, and this is quantum, and then I'm going to talk about combining the two. So we have our friend Bob. We have a magnifying glass, and we're going to zoom into his nose. A little fancy animation here. Okay, so docking theory. So this is the one that's traditionally taught, where we have an odorant, which is like a key, and then a receptor, which is like a lock. They bind together, signal transduction, we smell something, and it's like a non-covalent interaction, so like van der Waals or like cation, stuff like that. And then so the strength of the binding affinity will dictate the odor intensity. And so we're just talking about three shortcomings to using the traditional model. So one is there's chemicals with different shapes that smell the same, so that doesn't really work with the traditional model. Another thing is chemicals that have very similar shape, but then they smell different. And then we have chemicals that are identical, except that they have some isotopes. So in this example, we have cyanide, which classically has an almond smell. And then we have these two other chemicals that have huge planar rings, and it kind of doesn't make sense how their structures are very different, yet they all smell like almonds. And then another example here, and now we're talking about structures that are very similar. So here we have a quaternary substituted carbon, and instead we have silicon. Yet their structures going to be very similar, right? Because they're on the same column in the periodic table, yet their smells are different. This is camphor, which smells like medicine, and this is grass. So very different smells. Right, the silicon right there. And then we have isotopes. So we have this chemical that scientists specifically chose because flies were attracted to it. But when they substituted all the hydrogens with deuterium, which is just one extra neutron in hydrogen, all the flies were avoiding it. So very similar structure, and if we use a traditional model and think about how it binds the receptor, it wouldn't make sense because it's going to bind the same way, yet they were deterred by it. So all these exceptions make us want a new model. Yes, so we're going to talk about the quantum model now. So the quantum model is also called the vibrational model. So it was started by Malcolm Dyson at the time. You can notice this year was before the year of Erwin Schrödinger's book, so it wasn't really popular. People really shut it down. They really still prefer the docking theory. And so what the vibrational theory is about is we all know chemical bonds vibrate. If any of you guys took chemistry 261, you know that they can rock, they can scissor, they can do stuff like that. And so I know this one gives me PTSD when I see this these days because it pushes really hard. But the point here is every chemical has a unique resonance frequency, a unique kind of fingerprint. So we're going to talk about how the vibrational theory works. So there's 3 steps. We're going to talk about Raman Spectroscopy first. So what this is we shine a laser light onto the molecule. The molecule gains energy, it starts to vibrate, and it starts to emit IR, right, infrared radiation. And we always see that in our IR spectrum, right? The next one is quantum tunneling. So quantum tunneling is a quantum effect. Basically, every molecule in the universe has a de Broglie wavelength, and that's inversely proportional to its mass. What that means is the bigger you are, the smaller your wavelength. And so if you want a quantum tunnel, your wavelength, your de Broglie wavelength, has to be larger than the barrier you're trying to go past. So the smaller you are, the bigger your wavelength, which means you have a higher probability of kind of overlapping the barrier, and then you can tunnel through it. And so in this case, a really important thing to note is that the energy of like this thing, so in this case electron, very small, has to be exactly perfect. You can't have too much energy, and you can't have less energy. It has to be exactly perfect to tunnel over. So keep this one in mind. And so this is called elastic electron tunneling because there was no gain or loss of energy. It was the exact same. We didn't lose any energy here. Okay, and then we have IETS, which is inelastic tunneling spectroscopy. So this is how we think our olfactory receptors work. So we're going to combine the concepts we talked about, Raman spectroscopy and electron tunneling. So we take advantage of the fact that there has to be one single energy level. And so what we do is we purposely pump more energy in this electron, and what that means is we know it won't tunnel at all. So we keep this in mind, right? And then from Raman spectroscopy, we learned that when molecules absorb energy, they release it in IR, and that's an inelastic process because that molecule lost energy. And so when we combine the two, what we can do is place our unknown molecule here, and then we have our electron with a lot of energy, and then this molecule is an absorbate, and what it can do is steal the excess energy from this electron. And if it's the perfect molecule, it'll tunnel. So that's how we think our olfactory receptors work. Basically, a molecule has to have the perfect resonance frequency, which is unique to every atom, and when it does, it'll allow tunneling to occur. And so it's inelastic because this electron lost energy. It had a net loss of energy because this guy emitted IR. And so here are like two experiments that they did that kind of confirm this theory. So number one, flies. So using their theory, they found out using IR, right? They know that the resonant frequency for nitrile and like carbon deuterium bonds are very similar. So they hypothesized that if they're similar, maybe flies will observe them similarly. And so what they did was they conditioned flies to avoid deuterium, and then they randomly put in nitrile-containing compounds, and the flies constantly avoided nitrile-containing compounds. So this is really good evidence that this theory works, right? So we have conditioned stimulus, we conditioned them to not like deuterium, and then the conditioned response was they started avoiding this one. Another piece of evidence is, this is application now actually. So a big thing in men's fragrance is they like to put the fragrance sandalwood in there, but before that, it was really hard to get this odor into men's fragrance because the chemical that it comes from is called coumarin, but it's also a carcinogen, so it's like not ethical to put it in fragrance. You want to spare yourself. And so what they did was really smart. They hired a bunch of like biologists that were like supporting this vibrational theory, and they thought if we can match the resonant frequency of coumarin, we should be able to produce the same odor as coumarin. And so they did. It, right? And you can see it's very similar here, very similar resonant frequency. And you see the structure is really different, right? They added like another like 5-membered ring or something, and it gets trademarked, and so it works. Okay, let's talk about the major flaw of vibrational theory. And so this slide is also going to combine the two, because they both have flaws. So the biggest flaw for vibrational theory is that it doesn't take into account enantiomers. So these are like hands, right? They're exactly the same, except they're just mirror images of each other. But what that means is they'll have identical vibrational frequencies, because that's determined by the bonds and the atoms. They have the exact same configuration. So vibrational theory doesn't really take that into account. So really the overarching kind of idea here is that it's like a sequential approach, where we have docking, so transient binding of a molecule to the receptor, but the actual detection, like signal of what the odor is done by vibrational. So like inelastic electron tunneling. So that's what we think our nose is doing. But the docking is like the initial step that kind of helps us differentiate between enantiomers. And so now we can talk about the electronic nose. So unlike when you talk about like vision, we have like cameras. When you talk about hearing, we have microphones. And so these measure physical aspects of nature, right? Wavelength is very like definite. But when we talk about our odor, we'll notice that's really hedonistic. Everything we smell, we always have a judgment to it, right? Whereas what we look at and what we hear, sometimes we just ignore it. But smell, whether you're smelling a fart, tea, strawberries, you just get an instant, like good or bad. There's no like kind of in-between smell. And so that makes it really difficult when you're trying to make an electronic nose, an electronic sensor for odor, right? So smell is chemical, whereas like these are more physical phenomena. And another thing is like our olfactory capabilities are very inconsistent, right? There's no range. Hearing is like 20 hertz to like 20,000 hertz. Our vision is like 380 nanometers to 740 nanometers. But there's no kind of range, right? Which chemicals can we smell, which chemicals can we not smell? And so we can smell over 1 trillion distinct odors. So the progress of the electronic nose. So there's two routes we can take. So the conventional electronic nose uses chromatography. Chromatography is just separating out which chemicals exist that way. And so what we do is we separate out, we have all these chemicals, and then we have to build a neural network and a bunch of like complex algorithms, and then we get a bunch of humans in, and then they judge, was this chemical smelling good, smelling bad? And we build this really good neural network, and then we found that this computer could actually, this chromatography electronic nose could start predicting what we think is pleasant at an accuracy rate of 80%. So that's pretty impressive. Another option is bioelectronic noses. So in this case, there's two components. The primary component is going to be a biological aspect of our olfaction. The secondary is going to be the electronic thing that's going to measure the biological thing. And so previously I talked about how a major challenge was that receptors kind of degrade when you take them out of the cell. So this is a way of kind of bypassing that. Because what we do is we start isolating vesicles containing olfactory receptors as well as calcium ion channels. And so we combine them together. Let's see if I zoom in here. Perfect. Okay. So we have calcium ion channel and then olfactory receptor. And so the benefit of the calcium ion channel is it gives us amplification. Because depending on how tightly a molecule binds here, it gives us a lot of calcium ions, which means we get more finite control of how. And so what's that called? The electronic thing measures the concentration of ion released through like carbon nanotubes or something. It's pretty complicated. But ultimately we get a really sensitive signal to it. And so that's kind of works. We have a cell and then we kind of like isolate, so we just have the receptors. Okay. So that's the electronic nose. Now we can move on to the quantum nature of vision. So we have like 120 million rods, 6 billion cones. We'll go straight to single photon detection. So why do we think the retina is quantum? So they discovered that the photoreceptors can actually detect single photons. Now by definition, that is a quantum phenomenon because light is a wave, but wave-particle duality tells us that like light can also be a particle, so that's just quantum. And so how they found this out was we actually still can't really produce single photons, so they devised a really cool trick to show that our photoreceptors could detect single photons. So what they did was they had a weak laser and they knew how much photons that could produce. And then they targeted a specific region on the retina and they knew how much photoreceptors there were. And so they had less photons than photoreceptors. And the patients could still detect light. That tells us that a photoreceptor can detect 1 photon. But they did like complex statistics, right, to like figure that out. And then another piece of evidence that the retina does quantum events is there's a molecule in our retina called retinol, which is in rhodopsin, which is in our photoreceptors. So retinol is this, normally it's in this form, but when a photon hits it, it goes all to trans. So we have like a cis bond here, and it went all to trans. And so what they noticed was that it was super efficient at switching, and it was so fast. And none of our like classical physical theories could tell us why that could happen. It couldn't explain it. And so here's a quantum explanation. So they suggested that retinol was actually in a quantum superposition. So that's exactly like Schrodinger's cat, it's dead or alive. At the same time, this retinol is cis and trans at the same time. And again, same with Schrodinger's cat, where our observation triggers the collapse to a definite decision. So too is the photon. That observation triggers the retinol into its cis or trans state. And so this also explains why sometimes photons hit the receptors, yet they don't induce a signal. Perhaps because the retinol didn't change. So this opens up a new field. So we have quantum retinal biometrics. So biometrics aren't really a new thing, right? We have like fingerprint scanners, we have like facial recognition, retinal scanners. As cool as retinal retinal scanners sound, they only look at like just the specific pattern of blood vessels in our retina. And so the common theme between all of these is that they're not really guaranteed. They're still based on physical things, which means we can foil them. If we could like replicate the pattern of veins here, we could foil the system. So none of them are truly guaranteed protection. And so how does quantum biometrics come in? So there's a really cool technique here. We know that the photoreceptors detect light really imperfectly, and that's for two reasons. One is anatomically, our eyes are imperfect, and there's a lot of environmental complications, so that's one reason for imperfection. Another reason is quantum statistics, like we just talked about for superposition. Just because the photon actually hits the receptor doesn't mean it actually gets triggered. So these are two kind of like extra complications a person trying to do fraud would have to get past. And so no one can predict like quantum statistics. And so this combined probability, they call it alpha. And so alpha is unique in two ways, right? In one way is that everyone's alpha value is going to be different in any region in the retina. And another reason is that alpha value changes across the entire retina. Imagine your retina, they split into like 100 squares. All the change in alpha as well as every alpha value given is unique. And so this is really cool because what they could do is by knowing everyone's unique alpha value, they could put in a specific like pulse of photons, and only people with that exact alpha value would see the code. So this is an encrypted message now. This person could see too because their alpha value was some certain number. Anyone else wouldn't be able to observe the data. And so yeah, that is my presentation.
Questions?
If you didn't understand the science, you can ask me. I think I'm not sure if I explained it that well. Yes?
I have two questions. So the first one was about in the olfaction part. So just to clear up, you mentioned that a flaw is with dealing with enantiomers. So does that mean enantiomers smell differently? Like we?
Oh yes, did I think I might have missed that. Oh no. Okay, let's see here. Yes, okay, so I didn't mention that. I should have put that in. So, yeah, I was supposed to add an image here. So yeah, so our carbone, one of them smells like spearmint and the other one smells like something completely different. I forgot. So yeah, they have very different smells, yeah, so that's the thing. But we know that proteins in nature, they all have chirality, right? All our receptors have chirality. And so that's why the docking mechanism makes sense to be as the first step, because that would like be the filter. And then once we filter out the chirality, then we can do a very accurate measurement using inelastic electron tunneling.
But all of the molecules that we smell, they all go through like both of those steps.
Yeah, so this is what they're thinking, right? Because individually they miss the mark, right? But when you combine them together, it makes sense, especially in this order.
Okay.
Yeah.
And then I had a second question as well about vision. So so the retinol that switches from cis to trans, so that's you can only see or register a photon when it's one of the when it's trans.
Exactly.
Okay.
Yeah, so that's how I think you have to memorize this in psychology or something. I forgot, but yeah, it's I think it turns to trans and then it turns off the cell or something, and then it turns on another cell. I think that's how our eye works.
Okay.
Do you remember? I think you were.
I don't remember.
I don't remember. I think that's how it works. But yeah, all trans is like the thing that has to happen for us to like visualize the signal.
And then you mentioned it was possible for a photon to go in, but for you to not
Register it.
register it.
Exactly.
So it just happens to be in cis at that moment.
Yes. So I think that's where this like quantum superposition comes in, right? Like we could observe Schrodinger's cat, it could be alive or dead. Because if it was just based on classical physics, then if the photon hits it, 100% have to turn to trans, right? Like that's just how it should happen. But that doesn't always happen. And same with superposition, right? Just because I observe it, it could be dead or alive. So same with cis, it could be cis or trans. But I'm sure the percentage of it turning trans would make more sense to be higher, right? Because that's the photon's job. But yeah. Yes.
I guess with kind of like the e-nose and kind of that aspect, would it be possible to kind of change the reaction of how something smells to someone kind of with that technology?
How something smells to someone?
Yeah, so like, cause I know like for myself, like skunk doesn't really affect me. I don't know
Right.
why, but other people just find it just horrid. So like, would that be kind of something that you'd be able to tweak with someone with that kind of technology?
I don't know about tweaking, but I do know that there is a lot of articles talking about standardization for odor. So by using these electronic noses, which of course are going to be super objective, we can make like a standard of like, and we just put a code. So we still don't really get subjective data, but at least we have a code there. So then everyone can relate, oh, that's code number 203, right? So it's just like the color red, everyone sees red differently, I think, something like that. Yes.
Do you think it would be possible to perhaps implant one of those electrical noses, and then somehow get it to send the signal to the brain as an analog for somebody who perhaps got their nose like burnt off by smelling dirty chemicals?
I think that has to happen for sure, right? AI, they gotta have all the senses. Smell is certainly one of them. I have no idea how to do it, right? Because all these, I only show you the cool stuff, because when reading the papers, they have so many mathematical equations, like sigma symbol or something like that, like, I just skipped that part, right? I only saw like the cool part, so, yeah, it's a lot of math probably to like, do it.
Okay,
Okay.
great start.